Hello, welcome to EC31202. We are going to talk about layer 4, that's BJT differential amplifier design. Okay, so what is a differential amplifier? So it employs matched transistor pairs. That means we need two transistors and they have to be matched, and using those two matched transistors we want to create a stable circuit. So we'll see what is matched and what we mean by stable later. So let's focus on the matched part here. So a matched pair indicates that the transistors that are used to make the differential amplifier are generally built on the same silicon substrate using the same process. So they are really very similar. That means like if we have a transistor 1, and if we have another transistor 2, so this transistor and this transistor, they are built on the same substrate. Like if we are using the chip, so we are using the same chip. It's not like we can get the transistor 1 from this chip and transistor 2 from this chip. That is not going to be a very good match. To get a good match, we should get the transistors from the same chip. So if we take a look at the pin diagrams, you'll see like the transistor 1 might be here and transistor 2 might be here, but inside they are sitting on the same piece of silicon. So that's what we mean by match. They were underwent the same process, so they are really very similar. So because they are similar, it's possible to eliminate some issues, like they have everything in common, so we don't have to think about the bias stability, rejecting noise and beta stabilization individually. So if we can create a stable bias for one, the other will be stably biased. So if one is suffering some noise, the other one will have the same amount of noise, so we don't have to treat them individually, so their beta will be also the same. So using the same using the transistors from the same chip gives us these advantages. So just for your information, this is the fundamental building block of an op-amp. So we have seen op-amps in the past, and we actually wondered what's inside it. So this is actually the fundamental building block of op-amps. Let's go to the next slide. And differential amplifiers are typically used to amplify only the difference in the inputs at both the transistor bases. So as the name implies, it's called differential amplifier. So that's why we expect if there is a difference between the let's go back. So if there is a difference between the in the signal level in the transistor 1 and transistor 2, that difference should be amplified. So that's why we have the name the difference amplifier. And the common signals such as noise, we don't want to amplify that. So that's what we mean, like if we have the transistors having the same properties and if they have the same input, there shouldn't be any amplification. That's what we expect. So this is why these things are called the differential amplifiers, and the noise doesn't get amplified. In theory it doesn't get amplified at all, but in real life it does a little bit. So this is a good thing. We don't want the noise to be amplified. So basically we have two properties. One, there is a difference between the base voltages that's get amplified. It's really good. And the common signals such as noise, which appears at the both transistor space, it doesn't get amplified. That's also good. So that's what it is. That's a differential amplifier. Now let's see how the circuit looks like. So this is how it might look like. It's a very simple arrangement. You have a VCC, and we have the transistor 1 Q1 and the transistor 2 Q2, and then we have the inputs like the V1 and the V2, and they are providing feed to the transistor's base, Q1 transistor base and the base of the transistor Q2. So what about these V1 and V2? They can be same, they can be different, and depending on that, the output should be different, and the output is here. We can call this V out 1, and the another output is here. We can call that V out 2. So we can pick them from either of these two. So that's what it is. And here is some specification given. We want a gain of 25, and we want a quiescent point of DC of 25 milliampere. VCC is 6 volt, VEE is minus 6 volt. So that's what it is. Now we can actually operate the circuit in a single-ended mode. Like here we had the transistor, and we had the supply, the sinusoidal source connected to both the bases, but we can create a ground here. I mean, we can just eliminate this. So then the circuit would look like something like this. So here we have the same circuit. We have actually removed the resistance here. We can put the resistance here, and we have grounded one of the transistor's input. And just here, I just for the drawing in the SPICE, I just use it 2N222, but it's true for any transistor. I mean, if we are using different transistors, C3046, most probably that's what we are going to use, 3046. That would be in a package, but it's just an individual transistor that's I'm using here. So that's what it should look like if we are running it in a single-ended mode. Now, what we are supposed to do here, we have to design a circuit for mentioned performance, like the 25 gain and some DC current requirement, and we should use the H parameter model and simulate them in the HSPICE. The reason is, in LTSPICE. The reason is in the LTSPICE, I didn't see in the library that I was using had the didn't have the 3046, so I used the H parameter model and I used it in the LTSPICE. And if it was possible, I would like to use a actual transistor to simulate circuit in LTSPICE. That means like we shouldn't be using just like a generic transistor, like we shouldn't just pull down a transistor without any parameters, so we should avoid that. What we should do is we should pick a real transistor. I mean, it can be 2N222 or something like that, and after that we'd build the circuit on the board. And at this point I should say, if we use the LTSPICE and simulate with 2N222 and build the circuit with C3046, there might be some difference, but at this point we are okay with that. That's not going to be a problem for this lab. Now, for design, we will consider single-ended operation in which the output is taken only from one of the collectors with respect to the ground. So that means, let's get back. We'll try this one first, and we'll try the single-ended operation first, and we'll try to see what we have here. I mean, or here. So we'll be okay. We'll just looking for the single-ended operation, and we're not going to take the difference between here and here. That can be done too, but we're going to measure the voltage from here to ground. So that's what we are trying to say here. We are going to do the single-ended operation, and we'll take the output from one end of the collector and measure the voltage with respect to the ground, and outputs at each collector will be 180 degrees out of phase. So it's okay, we can measure either of those two, but one of them is okay. I mean, either of them is going to give us the output. So design, just take a look at the data sheet for 3046, and we find that HIE is 10.5 K. Let me change the color of the pointer. Okay, so HIE is 10.5 K, HFE is 105, and we take the RCS 5K. So using the KVL and all the recommended values we have the RE to be 10.5. so here the design is given for you. You just have to use it to get the results. And you can use these values in simulation in LTSpice and verify the gain is somewhat correct and use a meaningful input voltage source. That means like we can't just put any amount of value for the input. I mean, the input should be something that doesn't saturate the transistor. That's what we are trying to say. Like we should be using a meaningful input. We don't want to put like 5-volt sine wave with 1 kilohertz, because if there is a gain, it's going to be a huge value. Or we shouldn't be using like 5-volt at 10 megahertz. That's going to be a problem for the transistor. It might not be able to handle that high frequency. So we should be using something meaningful so that the gain and the input produces some output which is not beyond the saturation. Okay, then comes the common mode gain. It is the measure of the amplification of common mode signal. So if we have a common mode signal input at the base at the both transistors, so that's the gain we have, and it should be as small as possible to reject maximum noise. We don't want the common mode gain to be really high. So this is how it looks like, the common mode gain. What we have done here is we have connected the base of transistor 1 and transistor 2 together, and we have connected that to a single source. So last time, I mean, if you remember, we had connected a source with the base and another source with the base, and this time we are feeding the bases with the same source. So whatever we have here is also here, so they are in common, so they are running in common mode. So that means we shouldn't be having any output, but unfortunately it is not the ideal world we live in, so we'll be having some output at this point. So there would be something V out which is very small, but it exists. So the ratio of differential mode gain, which we just talked about before, let me just go over real quick. The differential mode gain is this, like single ended operation. We construct a circuit like this and measure the gain, and then we connect this port to that, not to the ground. We connect this base to this kind of voltage source and get something like this, and we get another voltage output. So there is another gain. So we have two gains. One is like when this is connected to the ground. Let me clear all this. So this is the common mode when the bases are connected together to a single source. This is the common mode, and if I break this line and connect it to the ground, then that's the differential mode in single ended operation. So we have two outputs, I mean two cases of the voltage output, and we have two gains, and those two gains give us a very important information. So the ratio of the differential mode gain to the common mode gain is an important measure of the performance, and it should be as large as possible. These are called the common mode rejection ratio, which is given by this formula, and if we look at the information provided by the transistor manufacturer, we can actually estimate the value of the CMRR, and this is the equation. And as we see, once the transistor is fabricated, this is already there and this is already there. The only term that we have control over is this RE. So when we are designing, we should try to make the RE as large as possible to get a large CMRR, which stands for the common mode rejection ratio. And the input resistance, these are the values. The derivation is in the lab manual, but we are just using the values in the PowerPoint. So differential mode input resistance is 2 times of HIE. Common mode input resistance is 2 times REHFE. So we should note that the common mode input impedance is much larger than the differential mode input impedance. Yeah, that's expected, and we can find the values from the theory, which is simulation, to compare with the values observed from experiment. So what we're trying to say here is we can measure the input impedance, like how much current is flowing in to the transistor, and the voltage we can measure the input impedance very easily, and we do the same while doing the implementation, and we can see how it differs. That is the ideal experiment, but unfortunately if we cannot have the 3046 in the LT-SPICE, then there should be the model mismatch and the simulation results may not be translated in real measurements. Just for your information. Now for simulation, what do we need? In simulation, at first measure the ICQ to see if your transistor is stable and biased properly, then measure the difference mode gain, difference mode impedance, just measure the voltage, input voltage and input current, and you can just divide and get it. Then common mode gain and common mode input impedance. It is very easy. You just draw the circuit once and you just connect it to the ground once and connect it to the source once. I mean the base, connect the base to the ground, connect the base to the source, and it's done. To test the difference mode signal, that's what I just said, the ground one of the inputs and apply a test signal to the other input. So that's the difference mode. And to get the common mode, just remove the ground from the first base and connect the wire to the test signal. So it's very simple. Like you have base connected to the ground, base connected to the source. After that, you get that to the source. So it's done. Okay, there's something to think about. When the circuit actually works, the difference mode signal is mixed up with the common mode signals. What does that mean? That means when we are actually when we are actually using this circuit, we have the differential gain, and actually the common mode gain is also there. There's something tiny, and these two gets combined and we get the output. So that's what it is. Like we actually really want the difference to be amplified, and whatever is common, we don't want to get that to be amplified. But unfortunately, the difference gets amplified, the common thing also gets amplified, and at the output we get their sum, something like the superimpose on each other, and we get the output. And when the circuit works, the common mode signal is unwanted. We don't want the common thing to be amplified, but it appears and it cannot be easily suppressed. So here is the circuit diagram again, and to just show you again what I just said, for the first measurement, remove this, short this. This is the differential gain. Like we can just measure the voltage we output here, and this is the gain we have with respect to the input. After that, what we will do is we are going to let me change the color real quick. Yeah, we are going to remove this and connect this line to here. So this base and this base, they have the same voltage and everything is common. So whatever appears here, it is unwanted, but we measure it, and that's the common mode gain with respect to this one. And then we divide each other, these two gains, and then we obtain something called CMRR, common mode rejection ratio. So it's a really simple lab, and that's it. All right, thank you. See you in the lab.